projective plane. So this is my P2. And we study curves, rational curves of different degrees. So this the degree 1 would be a line, degree 2 would be a conic, degree 3 would be a cubic, and so forth. So cubic, and so forth. So there's some moduli space and you can define it differently, but you can think of a moduli space of degree d curves as you have your own, somehow you have P1, and you look at a map of degree d. Rational. Yes, you can fix some genus. So let's say rational. So you look at so you have P1, a map from P1 of degree d to P2 given by 3 polynomials of degree d. So its image is going to be something like this. And then, well, you have to worry about what's going to have like a conic and break into lines. So then the domain will be, the domain of this map will have to break here. So there's all sorts of things how exactly you're going to compactify. But basically you can, and if you want them unparameterized, then maybe you want to mod out by the action of automorphisms here. Anyway, it's going to be some algebraic variety. So of dimension. In fact, it's easy to so if I study the dimension of moduli, so maybe so there are many algebraic varieties you define. I'll just write one of them. They all have the same dimension. So maybe it's m bar genus 0 p2 degree d. So this is the genus, and if you have marked points, you put marked points there. So this dimension of this is 3d minus 1. So for example, there's a, if d is 1, you have 2, and it's a dual projective planes, lines, and so on this variety there is a divisor, namely if I consider a point in the plane. So this is generically you're not going to hit that point, but in codimension 1 you are going to hit the point. So there's a divisor. So d curves meeting a given point. In P2. And the simplest question you can ask is the degree of these divisors. Namely, if a divisor of an algebraic variety, you can take its self-intersection, so you take it. So it's going to be, this will be a number. So this is a number of rational curves. Of degree d meeting 3d1 is 1 point in P2. And just a very basic test of somehow your feeling for this kind of things. How do you think? So if I plot this for d equal 1, say 1, 2, 3, say 4. So what's that number? So how many lines meet 2 points? Okay, it's easy. Okay, so then the next, how many conics meet 5 points? One, yeah, easy. So how many cubics meet 8 points? That's a tricky one. This is something you can. This is something you can do. What? No, 12. So that's a fun computation. Something you can do. And then, well, the next number you can work out is 120. But all of them are known. Much more is known. And there is the kind of this. You can ask many more general questions. So you look for moduli. So maybe M kind of moduli of maps from some curve B to some X. And this is SITS. This is something here. Here the curve itself was not so P1 is just only one P1. We have to only worry about P1 breaking. So there's some issue of stability and so forth, so maybe let's not worry. So this sits over the moduli of B. And so this is more generally you have natural on this class here. We have natural. So divisor. Well, the divisor in algebraic variety. You can think of this as an object as something defines something in the Chow ring, something in cohomology ring, but maybe the best is to think of this something in K-theory. That's the most natural thing. So it's a natural classes, natural K-theory classes. Here, and then you can push them forward, so you can kind of in other words, you have some modulo of your B, and you can, if you're physicist, you integrate over all possible maps to some variety X, and you get some, instead of a number, you may be able to get some class here. You can further integrate that guy here. So you push forward K-theory class. What do you mean push forward K-theory class? Means it's you take an alternating sum of all cohomologies of it. So if you push forward a sheaf, you're gonna get sections, but also higher cohomology. Take the alternating sum. That's the push forward in K-theory. And so then, of course, what's the so then what's the supply of interesting X? This is the of course in algebraic geometry. See this picture. They tend to substitute their favorite varieties here. So of course, projective spaces, homogeneous varieties are everybody's favorite. Everybody so somehow that's a good theory to study. You can in principle study a general algebraic variety, and so this is it's a valid concern. But since this is a workshop in mathematical physics, not algebraic geometry, and I'm also I consider myself more of a mathematical physicist than algebraic geometrist, then there's some X's that are physically more motivated than the others, and so in fact they don't need to be a variety, so to speak. Somehow if you think of how you define a modulo of maps to some target, then there's some. I think I'll strictly avoid any technical notions and know how you define moduli space of maps, what it means to how do you deal with different. I mean, already in this case, you see you have to do something, because a curve of degree d can break into up to d pieces. So this X. So from the point of view of mathematical physics, the interesting thing is X. So somehow the meaningful thing is the following, and one thinks of the B. B is the space of some 2 plus 1 dimensional. So there's dimensional quantum field theory. So this is we studied something 3-dimensional theories, but there's one direction which is kind of like time, and one is to space. B is something 2-dimensional. In X, that's maybe part of the moduli of vacuum in this quantum field theory. And the reason why I study this, that this is the integral in K theory, or what it really is, the Euler characteristic, or this push forward. So maybe I already know this pi. It's this push forward in K theory. What it really is, what it computes, what you compute this way, computes the index. The supersymmetric index. And how do one explain something like this? So suppose you have a so this would be, I apologize to my physicist friends, this will be an algebra somehow. Again, it'll be an explanation of the same level as I'm going to do as much justice to physics as I'm going to do justice to algebraic geometry in this picture. So it's so the beauty of what's a supersymmetric quantum field theory? Well, so in this kind of Hamiltonian discussion, you have some space and you have an evolution operator. You should think of evolution operator as something like Laplace operator, maybe in some infinite dimensional space, and then it's supersymmetric if it's a square of some other odd operator, something like a Dirac operator, and that this Dirac operator changes parity, sends something of even fermion parity to the odd one, and then you take the index, which is you take the index of the operator. You take the dimension of the even. You take the even part of the kernel minus the odd part of the kernel, and the beauty of an index of an operator is that is deformation invariant. You can compute it in any, say, you have some space of parameters. You can compute it in any corner of that space of parameters, and in particular, you can look at the lowest possible energy states of your theory, and this you can try to describe by modulated vacuum. So if you have exactly lowest possible state, then this is something which is like state exactly the same as in infinite space. You think of B as some infinite space, and then the next approximation would be you try to think of modulated. I mean, vacuum depend on parameters, and they kind of change. Like for example, in my if I have a gas, then a steady state of a gas in an infinite volume would be described by what density of particles and the temperature. And if I'm in a finite volume, I'm going to describe like a low energy state of a gas, and I think of the density and the temperatures as functions. So I have a map from my space to the moduli, and this is. And then so then the kind of theories we want to consider is that for them X is something like some object. There's no somehow in algebraic geometry we're still struggling to define the right kind of X. So there's something like which what it should be. It should be some kind of nice, but in general singular algebraic symplectic. There's a close relation between algebraic symplectic and hyperkähler. Kähler variety. There's an actual issue here. There's a class of varieties called equivariant symplectic resolutions that people like, but it's clear that this is not. I mean, as a definition, it's not the right class. But you should think that there's a certain interesting class of algebraic symplectic varieties that in general will have singularities, and then there'll generally be some discussion what it means when variety is singular. Then this moduli. I mean, anytime you have a singular variety, this even for a smooth variety, this is a very singular object. And you have a singular variety. Many constructions really go, really. I mean, matter standard construction algebraic geometry assume X to be smooth. So then there's some deep technical issues how this should be defined, but a good theory in particular. So a particular good theory. So good theory exists when X is algebraic symplectic reduction. Namely, X can be written, so there's some group, maybe there's some group G, X on this is smooth symplectic. Then, so if it's a group acted in symplectic fashion, there'll be a moment map, and algebraic moment map, and then you set X to be the algebraic symplectic reduction. You take the zero fiber of the moment map, and you take a GIT quotient by G. So that's a smooth symplectic affine. Then there's good theory, but the point is that there are many varieties that we would like to put here. We don't know how to write like this. And the simplest actually in representation theory is the source. I mean, classical representation theory is the source of great many examples. Challenge to present something like this. For example, if I take T star, so everybody's favorite symplectic algebraic symplectic variety is T star of a flag variety. If you go outside of type A, it's not known how to present it in this way. In type A, it can be presented this way, and outside it's not. So to present flag variety is a quotient, is a algebraic symplectic reduction by a reductive group. So that's unknown outside of type A. What? Yeah, I don't know any abstraction to that either. Yeah. So anyway, so somehow there's a good theory of this modular in this situation. In general, there's some kind of gap. And of course, a singular variety like that need not have a symplectic resolution. So it's while you can meaningfully study this, it's already here. It's clear that the class of current symplectic resolution, while very important, is not the right class. What? Yeah, of course. Yes, of some, yeah.
So every point of B has its own x.
No, why? I mean, there's some. I mean, no. No, it's like saying, there's density, temperature. That's something universal, independent of where in my room You can twist it. You can twist it. If you have some global automorphism, you can twist it by global. You can somehow have some gauging, but otherwise it means. Yeah. P is a space. B is physical space. Yeah, it says space. Oh yes, yeah. Sorry, it's not. Yes, it's not the space of theories. It's actual space. Yeah, is that? B is two-dimensional. Theory is 2 plus 1 dimensional. Then you associate in 2 plus 1 dimensional theory, you associate the Hilbert space to a time slice, to something two-dimensional, to the B. That clear?
Your X has constant structure, right?
Yes. Yeah.
Which constant structure?
To standard T star. I mean, if it's T star, so it's T star of flags has the standard symplectic structure of any T star. T star, yes. So nice singular algebraic variety. So that's maybe EG nilpotent cone. EG nilpotent cone. So many people spoke about it, and so then the resolution of nilpotent cone is T star of G mod B. So I guess if you write it, yeah. So this is. And so what's the main example to have in mind? The main example that goes beyond the classical theory is, yeah.
So now you draw arrows. So which one is X, which one is Y? N is X and T star.
No, there's neither of them. They're kind of both X. I mean, when you. So this is if you think of this is a singular affine Poisson variety. This is symplectic resolution. Not necessarily. The way the math are constructed, you don't use the resolution. You use this kind of presentation. Well, yeah, of course, here I'm computing something. So if you have an actual quantum field theory, this index like this is a very, very tiny part of that. I'm not insisting to have a whole theory defined to compute it. For algebraic geometry, it's enough to have it. I mean, for algebraic geometry, all you need is some kind of virtual A-roof genus of this manifold. That's all you need. You don't even need the actual Dirac operator. All you need is some element in K theory, that is, you can declare the A-roof genus of this manifold. That's all you need. And this is somehow this is extremely. I want to say this is extremely singular space that doesn't have a Dirac operator in the usual sense. So then it only has some Dirac operator in some virtual sense. So what's the main example? The main example is well, maybe main example for this talk is that when X is the Hilbert scheme, you take C2 and you take n points. So these are ideals. This parameterizes. This is the set. This is ideals I in the ring of polynomial of two variables of codimension, of finite codimension n. So a typical, of course, a typical ideal here is just function vanishing at n distinct points, and so then this is an open dense set in this manifold. And so then you can write that it is of the form of something mod GLN, in fact, by Nakajima. It's an example of Nakajima variety, and the Nakajima variety is something of this kind of form. And it is so it is a modular or Higgs branch of the modular vacuum in some UN gauge theory. But maybe more importantly, then this is also if you study the right kind of maps. So the right maps, maybe my whatever modular which I didn't specify, Bx. What this really is, if you come up work with the definition, from this part there's some moduli space. You work through this definition, this will be just the PT space. PT space is some version of Downson. So there's something called Downson-Thomas theory. This counts sheaves on three-dimensional manifolds. And in the world of sheaves, there are many stability conditions, and there's in particular chamber studied by Panderipante and Thomas. So this is a special case of some PT moduli space. This counts sheaves on a threefold of the form, just B cross C2. It's a threefold. And so this kind of computation is really what we're computing would be a k-theoretic Downson-Thomas count of this threefold here. And also, since you have it, you can have so a map from B to X is an example. So a map from B to X is a section of a trivial X bundle over B. But you can twist it. You can have like a section of a twisted X bundle over B. So then, by the same token, you can study PT Downson-Thomas theory of any bundles over curves. Yeah.
I'm confused with 1 and 2. So their dimension of B was 2, but it was real dimension, right?
Real dimension, yeah.
Now it's complex dimensional.
Yeah. In which part of that are you confused? So this really gives you there's a path, there's a kind of a clear path for them you can compute. In fact, this contains all k-theoretic. Take DT count for threefolds. It's also this theory. It's also this what maybe I'll say it's kind of interesting. This same, if you think of this as this three-dimensional quantum field theory, it's also conjecturally the same as the theory. The theory on the stack of NM2 branes in M theory. In a way that so I'm not going to explain. There's no way I can explain what M theory is, but M theory is a certain 11-dimensional supergravity theory. So it's going to be 11 dimensions here. And instead of so this has the fields of that include the metric, it's super partner, but instead of so in gauge theories we have a one form, just like with respect to which a particle is charged with respect to one form, then means you have to integrate this one form along the world line of a particle. Instead, here there's a three form, and the objects charged with respect to these three forms are this this membranes, which is going to be of the form maybe. So there's some, there's some this B, and then there's a time direction, which maybe we may take to make it compact. Let's make time periodic. So this is a 3-manifold. And then the way what's my time budget on this? The way this maybe it's this 3-manifold will have eight transverse directions in 11 dimensions. And so the way to think of this, the transverse, so this is my, so there'll be 8 transverse directions. The way to think of them is 4 complex. So there's 4 complex directions. So with 2 of which are this C2. And then the two remaining ones, so this C2 is that C2. So this C2.
11 minus t, is it real dimension or dimension?
So this is 3 real, this is 11 real. And then the transverse, I think, of 4 complex dimension, and 2 of which are just really this C2. And then 2 more, to tell about what's going to happen in 2 more dimensions, I have to say that this is, when you do this, this is, you should have objected before that this, how can I push forward something with respect to a map which is very, very non-proper? And the reason it's non-proper that this moduli of maps, they're only proper once you fix degree, but the degree can be arbitrary. Right? Do you have a, so for this example with projective line, you can have maps of degree 1, maps of degree 2, maps of degree 3, and so forth, right? So there's infinitely many moduli spaces that sit over this. So when you push forward, you need some variables to keep track of that degree. And so maybe what you do is you introduce here what you push forward is you introduce some variable, maybe call it z, to keep track of the degree of the map. And degree of the map is really an element. So what's the degree of the map abstractly? Degree of f. This is really the push forward of the fundamental class of B. And this is an element in second homology of X. So this is you should think of you can think of this monomial as being a character of the torus in which this is the character lattice, and then the co-character lattice will be second cohomology. And so then you push forward s times whatever before, and this is well defined. This will be an element not in K theory of that, but in K theory of that a join series in Z. So it's a series in Z with values in K theory of this object. So so here this variable Z, the way it's going to work is that the Z will become an equivariant variable. So there'll be these 2 remaining directions. Here, Z will really act. So this is, so maybe I'll look for some other color of, I guess I have only three choices for color here. So this variable Z here, we'll make it yellow. In this picture, what I want an action of Z. So here it will act by a matrix multiplying the first coordinate, the first of this remaining coordinate by Z, and the second by Z inverse. So this is the main point. In some sense, this is the main point of the main philosophical point, is that when I compute in K theory, the resulting computation in K theory is a virtual vector space. This virtual vector space is a representation of all symmetries in the problem. So in particular, if something acts on this transverse 4-dimensional complex space, that object will act on this will act on all of my computations, and this will be a representation of this torus. And what as a representation of this torus, it will have certain weights, and these weights will be, in fact, if I somehow expand them in a series of z, here they will correspond to computation of fixed degree. Maybe one more time. So when you consider this computation, or you consider this index, so when you compute this index, this is a representation. There's a representation of all automorphisms. So it's automorphisms of X act here. But it's also by via this is also, since I weight contribution of a given degree by a monomial in Z, I can formally consider this as also representation of some torus Z, which abstractly is for this varieties there's no difference between Picard and H2, but maybe to be specific, since this is if this is to be my lattice of characters, then my torus should be times this is a torus for which this is these are the characters. Yeah.
Why? Because there's a lot more automorphisms here that are given by GN.
Uh-huh.
And is there some philosophical reason why you don't have to worry about, for example, some affine transformations?
So affine transformations are not so interesting. That the K theory of that is somehow if you have any group that's in the K theory, you just might as well go to the reductive part of that. Yeah. So this is. Yeah, in principle, it is a representation of everything. Yeah, but very often in computation we just restrict to a maximal torus here and just keep with this torus and don't worry about the rest. So if you have a K theory of algebraic group, you just might as well restrict to maximal torus. And so then, what this picture is saying is that this part, if you view this from the M-theoretic perspective, this part plays exactly the same role as this part. Because it's just from the perspective, if I membrane with 8 transfer direction, there's really, from the 8-dimensional perspective, which is really no difference between the first 2 coordinates and the second 2 coordinates. Is that means on this Hilbert space there's an action of GL2. Obviously, right, because it just acts on everything. Inside of GL2, I have a torus. Maybe I'll call it A. This is a torus of the form A inverse. This is the maximal. This is the maximal torus in the group of this is automorphisms, and this is the maximal torus in the group of symplectic automorphisms. And then it says that this torus here and this torus there are just play exactly identical role. Right, the theory is really the curve counting variable and the variable that records the equivariance are just identical. I mean just symmetric, yeah. Well, there's some attempt to define what would be for a Calabi-Yau fivefold. There's some attempt to define what would be like counting of M2 branes in it. Yeah, there's some. Is there a 10-dimensional version? Yeah, this essentially it's a you take 11-dimensional of the form Calabi-Yau fivefold cross S1, and then there's a search which I guess Nikita and I started. There's a search to define this index of membranes in it. Supersymmetric membranes as some kind of algebraic geometry problem.
So is there a 10-dimensional version of this story where you start around +1?
That I don't know. I mean.
So you started with a 3-dimensional theory on B, and then you looked at the space of maps to X.
Yeah.
Now I could have looked now at the sigma model of maps from B to X.
Right.
And I'll get a theory now, a 1 + 1 dimensional theory. So is there any relation between this 1 + 1 dimensional theory, the original theory of?
Yeah, so there's some that 2-dimensional theory is like a limit of that K-theoretic stuff in Dukkha homology. Yeah. So there's also some. Yeah, so there is some, it's a very interesting subject how to actually define this thing. So this is, maybe I've, the right way to do this index in M theory, I think mathematically hasn't been defined yet. So there's some proposals Nikita and I proposed, and then there's some other proposals in the physics literature, which I'll be happy to discuss, but but maybe since we're going to go back to the world of three-dimensional theories, maybe this is best remains as an example. What is an example of? It's an example when you do counts, and you have, again, you do counts and you keep track of two things. You keep track of the degree of the map, and you keep track of how the automorphism effect acts. And the resulting counts are symmetric with respect to exchanging one variable and the other. And so then, the basic expectation. What?
You have here a torus A and you have a torus B. Do they commute?
You mean the way it's written here or there? They obviously commute. Yeah.
But so this should be not be a direct sum, but a tensor product of two-dimensional times two-dimensional.
No, it just says again, the normal space has 8 real dimensions, or somehow we should think the supersymmetric, say my 11-dimensional space-time is Calabi-Yau 5 cross S1, and a supersymmetric membrane, and it's an algebraic curve, and then its normal directions are four-dimensional complex directions. And so now in this 4 transverse directions, I have an action effect of SL4. But in this SL4, I have a subgroup like this and a subgroup like that, acting in the first 2 coordinates and the last 2 coordinates. And they play exactly symmetric role. And they commute, yes.
This is not.
Yeah.
But can you also comment what these letters PT and DT?
Well, DT means Donaldson-Thomas is some theory of counting sheaves on threefolds. But when you do moduli of sheaves, there are many different stability conditions, and there's one particular useful one proposed by Panaripanda and Thomas, and so this is particular moduli space. Other questions? And so this is somehow basic phenomenon. Basic phenomenon. And this is much studied phenomenon. It goes back to, I guess, Intraligator and Zyberg is the and there's really lots of work in this. I'm not going to do justice to this. I mean, I haven't been doing justice to anything I've said, but so in particular, I'm not going to go through the theory here. The basic phenomenon is that this theory is, common pairs. Common pairs. Such that if I have X is one branch, maybe means this is, maybe say Higgs. At this level, Higgs means just how, just some characterization in terms of supersymmetry algebra. So Higgs branch of the moduli of Akia. Yeah. And then this will be exchanged by for theory. This is the, and then there'll be X check. This is the Higgs branch for the dual theory. Maybe. So maybe I'll write it like this. There's the theory. And the dual theory. Where there's, take a moduli of Akia. there's certain branches that called Higgs and Coulomb here. Higgs and Coulomb. And this is X here, and this is X check here, X check X here. So it gets exchanged like that. And more importantly, for us, the curve counts in X coincide with the curves counts in X check with the exchange of this of the equivalent variable. So maybe this they take this torus A, which is the maximal torus in symplectic automorphisms of X, is identified with the torus Z check, which is H2 of X check Z O times C, and vice versa. And the two counts here and there are identified with the identification of these variables.
When you say Higgs and Coulomb, is it low energy and high energy?
No, that's on the. So this is there'll be a different lecture about it. Yeah. All right, and the example the Hilbert scheme that says this is an example self-dual, and that is supposed to be like the Langland's duality of the 21st century, because an example of that, if X is T star G mod B, then the dual is T star G check mod B check. And in general, there's some kind of roots. There's some kind of roots and whatever roots and dual roots associated with these two data, and they get exchanged and some other data is exchanged. And so now in general, it's easy to imagine that this is not going to be, I'm not going to present you a theorem today, a complete theorem today, just because I already told you that there's no, even beyond a certain class of X, we don't even know how to exactly properly count curves in X. Like for example, if I ask you, what would be the curve counting functions for T star G mod B and the dual ones? Then it's clear to everybody this has to do with Macdonald theory for the corresponding Macdonald polynomial theory for the corresponding types. And there is on the level of formulas there is such duality in Chladnick theory, but as we speak there's some slightly ugly definitions for this particular instance. There's some slightly ugly definition of the right moduli spaces, but certainly not no right ones, because we don't know how to represent this in this form, for example. So so what I will discuss today is a case when it actually can be done, and in particular cover the Hilbert scheme and many other examples. So somehow best possible case. So best possible case, this is has certain features, namely when both X and X check are of the form. So first of all, they're of the form of this form, and also have finitely many. So when you have a torus, if you have a torus, so this is you can ask, well, how can this be possible? Because it could be the case that there's some varieties just don't have any torus automorphism. There's somehow nothing to do on the other side, and but this is. Well, maybe let's not. Maybe I regret saying this. Maybe let's not go this. Also, a finite set of fixed points. So it means also dimension of the fixed locus here equals the dimension of the fixed locus in the dual geometry, and equals to 0. So just isolate the fixed point. Then one can make the following definition. So this is definition. This is Yeah, and this definition will cover the Hilbert scheme and cover many other things. So then we say X is dual to X check if you take if I take so maybe let P be a fixed point of the torus action X. It's a point, and so then but then this means if you have a fixed point of a torus action on something like this, then P is also written of the form this P is also a reduction by some other group, by some other reductive group. Just because in this form you take the fixed loci, then this will be a presentation like this. So it's a point, but it's a point written in a non-trivial way. It's a point written as an algebraic, it's a JIT quotient of some algebraic variety. And so in particular the curve counts in that P they're non-trivial because what does it mean? What does it mean you count curves in the quotient? Counting curves in the quotient is well, there's some data. So it's like a map to the quotient is a map. It's a principal G prime bundle together with a section of some associated. So if you have some. So what's a map here? It's a principal bundle with respect to this group together with a section of associated bundle by this guy. So in principle, non-trivial algebraic variety in particular has non-trivial degrees. So curve counts in P. So this will be this object. This lives some series. This belongs to series in X in Z. There are no more A's. It's just you killed all A's because you want to fix points, but it's still a series in Z, and that should be then equal to something which is there's no more degree variable, just only covariant variable. This is expressible in terms of character. So this has to do there's a way to express this in terms of the character of the Z, that is to say a check action on the tangent space at the dual point P check. So on the one side, you go to fixed points. On the one side, you kill all the covariant variables. You just left with degree variables. On the other side, you have just the tangent space. You don't do any curves. You just look at the character of the tangent space. Like for example, for the Hilbert scheme, what would it mean if I take a partition? That will be a fixed point of my action. Then on the one hand, this action of a torus in the tangent space of partition that has some expression in terms of hook length, some formula with hook length, and that this formula in hook length should also be equal to the curve counts, which is just go to that point. What? No, it's the same mu, yeah. No, not the same. Not the same. Mu, you want a mu prime inverse? Yeah. It's a restriction of the previous mu to some sublocus, but it's not. Yeah. And so this is maybe. No, it means for every, so this is for every P there exists dual P. So do you want a bijection? You want a bijection between P and P check such that curve counts in 1 gives you this. So that's a that's a definition.
So that's the condition of the finite number of points, right?
Yeah, that's the definition, yeah. And so then I should say that this can be this stuff, so this stuff can be analyzed. This can be analyzed. Effectively. The reason is The reason is that this curve counts, there's some theory about this curve counts. I mean, there's some theory about this curve counts, and the and they're expressible in terms of solution of certain Q-difference equation. And the order of this, I mean, this is first order Q-difference equation of the same size as the K-theory of X. So in general, it's some, if you have a, the K-theory of X has of some, some rank R, this will be R by R Q-difference equation, and something where there's some room for this to be something interesting. But if X is a point, then that means this is a solution of a certain 1-by-1 first order Q-difference equation. And so this is some real elementary, this on general grounds, this will be an elementary function. And this elementary function U has to do with this character. What?
With this definition, the dual, is it unique?
Not sure what the definition, no. So then, yeah, that is a theorem. Yes, that's a theorem, yeah. So theorem. So theorem of Minaga-Nagichinai.
And when you say curve counts, you actually mean this PT stuff?
No. This means anytime you have a presentation like this, there are some certain moduli spaces called so I don't know. They call different things in different math. They're called quasi-maps, and so that you do this have a PT space is an example of a quasi-map space. PT space is a quasi-maps to. I mean, PT space for a threefold that I wrote down. That's quasi-maps to the Hilbert scheme of points. Yeah.
That sounds like you're saying that somehow equivalent homology of X check
Uh-huh.
relates to Gromov-Witten theory of X.
They.
With those characters on that side is equivalent homology of the torus acting on X check.
So maybe I'll say a few words. So then it's. So when you do, kind of curve counts in X, this is an element. This is an element in where you take you have some you can impose. So when you do curve counts, you can impose some conditions, and like your curve meet a particular. Like we were imposing a condition to meet a point. This will say you take some conditions. From the K-theory of X. So you take maybe there were some automorphism equivalent K-theory of X. You may impose many conditions like this, or maybe some number of times, and then formal power series in Z. And then so this is one side of the equation, and then in the other side, if you take in the dual geometry. You similarly do X check some number of times, but now in the dual variables. And now the statement is that with a certain identification, that is not exactly sends fixed points to fixed pointers, some slightly smarter identification. In principle, if your fixed points are in bijection, this gives you a certain identification of the strings, but this is not the right thing to do, but with some other identification. This expression become equal or equivalent in a certain sense. I'll describe in a second. I mean, the best case if B is compact curve, not just equal. B is non-compact, then there's some issue. Not the issue, they're actually the heart of the matter. Does that then? Yeah. So this is then this is with this definition.
Is it the same all
What?
All is it the same?
No, it's not. This is like this automorphism here contains this torus A, and this contains this torus A check, and the quotient is actually the quotient some one-dimensional torus. I mean, the maximal torus here, modulo of this, is a one-dimensional torus that is identified in some special way. Right? With this definition, this
M is M the same?
M is the same, yes.
Where can we see M on the left hand side? What is M?
M is like you impose some number of conditions for your curve to meet. I mean, you just put some insertions. Or it's if you want to, somehow have M insertions in your 2+1 dimensional QFT. You put some boundary components, line operators. There's M of them. So so with this definition, there is an equality. There is a of curve count. And in particular, so part of the theorem is that this relation in fact is symmetric. So if this is the way it's written, it doesn't look symmetric, but in fact it's symmetric. And there's maybe I'll tell you the main. So I still have 3 minutes. So the main ingredient. So there's main ingredient is identification of monodromy. So there's some. These are both described by certain. This is general theory. They're by certain Q difference equations. So in the ordinary two-dimensional sigma model, that would be the old quantum differential equations, but here it's a difference equation by certain Q-difference equation, and the main difficulty is just to identify this. So need to these are the same. Need to prove these are the same. And the way to prove two difference equations are the same is a good first step is to prove that they have the same monodromy. So this is need to prove the same monodromy. So main step, main ingredient. So same monodromy. So this follows from so for monodromy of this Q-difference equation, we have an explicit description under this assumption. The monodromy of this, I mean, in general we have also some description, but it's less explicit if you don't make this assumption. So under this assumption, this monodromy is really explicit, same monodromy and explicit. So monodromy is computed in terms of something we call this elliptic stable envelopes. Which are roughly like maps from like elliptic homology, elliptic autointegral of the text locus to elliptic. And so one needs to prove an equality of the kind that if I take like there's a composed, so this is an interesting map, this stable envelope, and then there's a restriction map, just a functorial map, elliptic homology. And what one needs to prove, so if I take like a stable envelope of some point P1 and restrict it to some point P2, I get a matrix of elliptic functions, and one needs to prove that one needs to equate this with the stable envelope of P2 check restricted to P1 check. One needs to symmetry like that. And the way we do it, so this is and the way we do it is the following, is that we in fact we design a special class, and this is some kind of important thing. So maybe I'll write it down and I'll stop. So suppose you have two theories that suppose you have two theories that they're just different description of the same underlying reality. Then this means then in both theories then it means you have a very special boundary condition when you cut your Riemann surface along, you cut your space. It's like it's like a state boundary. The same people live on the two sides of this boundary, but somebody drew this boundary. And then this life is the same, but description is different. And so that means there's some interface on this boundary. From the point of view of the two theories, it's an interface, but it's an interface that does nothing. And so that means there should be a duality, like a duality interface. That should be a boundary condition in both theories. That's a boundary condition in theory like this. Well, I didn't have time to talk about, but it's easy to imagine. So you have a three-dimensional theory, on the boundary of that, it's going to be a two-dimensional theory. And in fact, if I'm thinking of geometries of the form curve cross S1, on the boundary it will be S1 cross S1. So it's just really a torus. And what lives there, it really, the way to think about it is that an element in that elliptic homology of that this the index and that boundary theory is an element in elliptic homology of X. It's some, and so this is what we construct the duality interface. That we construct it as an element in elliptic somehow out covariant homology of X cross X dual, and with the support there is this very special subvariety in X cross S check. So there is a subvariety that like you take all these fixed points which you have identified. So this you have identified fixed points. But then once you have identified fixed point, then you can take so if this is X and X2, you identified fixed points, you can take the attracting manifold on both sides. So this, since you have on both sides you have a torus action with isolated fixed point, you can take attracting manifolds on both sides. This will be a Lagrangian submanifold in this. This is a particular Lagrangian submanifold. And what we prove is that there exists unique elliptic homology class with this Lagrangian support, and when the elliptic homology class has some more data in it, it's not just support, but some kind of automorphic conditions, and that these conditions are satisfied, this is the duality interface. Once these conditions are satisfied, then you see just restricting on vertical horizontal slices, you get something that satisfies the conditions of stable envelope. The way stable envelopes are defined by some support and some automorphic condition. And so then you see that there's a unique class that gives you that. Now the restriction, this guy follows from the fact that this kind of duality interface on this product that gives you, if you look at it vertically, it gives you stable envelopes in one, and if you look at it horizontally, it gives you stable envelopes in the others. So this is, well, now I'm well over time, so I'll just stop.
When you say monodromy, loop and where?
No, so monodromy of a Q-difference equation is you take a solution. So, well, let's say Q-difference equation one variable. Then it has two singular points at when the variable is 0 and the variable is infinity. And you take solution at 0 and compare it with solution at infinity. This will be this will be a meromorphic function, elliptic meromorphic function. So monodromy Q difference equation is a matrix of elliptic meromorphic functions.
So I wonder if I got this right. So again, if you start with a sigma model with target, let's say, hyperkähler manifold, somehow I can make that hyperkähler manifold into the space of backbone of a three-dimensional theory on my original sigma.
Right.
This is what you're doing. But then I'll expect the Hilbert space of that three-dimensional theory to be the space of covariance of my sigma model for sigma. Right?
I don't know. I'm not sure. I mean, usually it's like some kind of so if you really, and if you somehow look at the way this computation are defined in math, it's usually some integral over the moduli spaces of modular space of maps into whatever x.
Right.
Yeah. So that's whatever the kind of yeah.
The thing is that I don't see how this torus appears. Unless you're
Well, you can take it. No, you can take it. No. So you mean which the degree torus or the?
Yes. So the degree torus, how it appears on the sigma model side.
Uh-huh.
I can only I wonder if there's always a torus acting on the space of covariance of a sigma model. This I only see if your target is hyperkähler.
No. It's just so the way it comes in the sigma model is that you typically have something weights by the area, right? The area. No, there's some weight of the area of the map, right? Then the area is proportional to degree. Yeah.
But in your last example, you talked about physical space, not P, right? Duality there, and this duality space is P, not max.
So it's the right. So so maybe I'll say it like this, and then we have some kind of there's some category of boundary conditions boundary condition in our original theory in our QFT. So this means I have my curve B, and there's some boundary. So then we'd like to associate something to the boundary, and very approximately, you should think of this as like coherent shifts, or some kind of Koch of loops in X. It's meaningful that there's some if I have a loop right there, and this is a meaningful statement, and there's the K theory of this category. This has a natural map into if I think of this. If I think of this torus as being, this loop as being Q being a loop rotation, if I grade an element by grade a sheaf by how this loop rotation acts here, what I'm going to go to a map to like a K theory of X, and then formal power series in Q. Right? And that this element, then one should think of this as a Q expansion of an elliptic function. So this is really an element in. So this you should identify with an element of with something in elliptic homology of X, where Q is this where my basic elliptic curve is C star mod Q. So this is how elliptic functions are naturally. So if I compute, like if I work with the K theory of this category, I naturally work with elliptic functions. An elliptic functions are the geometric way of them is they sit in this elliptic elliptic homology of my x.
Okay, so in your Hilbert scheme example,
Mm-hmm.
this action is dual.
Yes.
You pick up the torus. Is it related to some geometric structure on C2 which you didn't mention? Or
No, so this automorphisms here, the automorphism, there's a following exact sequence. So there's a the automorphism, the symplectic form here is maybe I'll write it here. So take automorphisms of x. They just go to C star. This character is defined, usually denoted H bar in the business. This is just by scaling the symplectic form. The symplectic form is unique up to multiple, so any automorphism will scale it. So this for JL2, this is the determinant. And then the kernel are the symplectic automorphisms. Automorphism x omega. And A sits here. So then the identification of the variables is that H in one variable is roughly, the example of how this should be done, you think of this 5-dimensional example. Then there has to be the product of 4 variables has to be 1. So this is this is H in one theory is roughly the dual. H dual is it's not in fully coherent theory it's not exactly right, but this may be something like this. That's the identification of the variables.
my question is about the other side.
Yes.
Do you have any structure on X which it's not X, on C2 which chooses with A inside SL2?
It's a maximal torus. You can compute computation in a coherent K theory, somehow SL2 coherent K theory is just the same as computation for maximal torus. Just the natural map is injective, and so you can pick any maximal torus you want.
Андрей, если все-таки вернуться к тому примеру, с которого вы начали, да, там самый full difference equation есть, он тот. Даже вот когда мы просто хотим посчитать эти самые рациональные. Нет, там будет то есть там просто не full difference, а просто. А все-таки реально, если я хочу чисто посчитать, то должен что делать?
Нет, эти числа они же какой-то минимум. Он как бы абстрактно
Ну, а если все-таки прямой вопрос задать? Вот как самым простым образом мы считаем эти числа?
Есть такая вещь, там
Здравствуйте, вы на меня забыли, да? Александр, мы в Рио-де-Жанейро как-то вам встречались. Мы даже с вами пишем.
Да, я помню.
Вот я хотел вам, может быть, вы не любите читать на компьютере, почитайте, какими замечаниями. Я хотел ее такому.
То есть предыдущий случай.
У меня лежит бездна замечаний. У меня просто лежит этот текст, весь покрытый чернилами.
Да,
Но я вам что-то написал по этому поводу, но вы не ответили.
этого быть не мог, потому что я все очень... Вы его мне выслали фотографию или как, если у вас он там лежит, как я вам могу сделать? Или вы...
Я написал, что он есть, ответа не получил. Теперь,
понятно.
наверное, можно просканировать легко и послать.
Ну да, фотографируйте, сканируйте. Я это самое...
Да нет, конечно, он у меня просто весь покрыт этими чернилами.
Ну отлично. Ну, значит, я вот еще что хотел.
Да.
Я вам оставлю.
Да.
Раз уж вы такой любитель. Это элементарно. Элементарно. Ну, прочитайте.
Хорошо, спасибо.
I mean,
Я
I just
специально
entered spaces.
написал,
So
что,
they put this
как
paragraph.
говорится, когда говоришь, вот что-то забывается, что-то нечетко. Ну, понимаете, Я уже с многими там, даже с большими людьми разговаривал, что-то там